Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So let's dive into today's daily challenge on Leetcode and see what's there. So we have the lexicographically smallest equivalent string. You are given two strings of same length S1 and S2 and a base string also. We say that each element of this S1 and S2 are equivalent. The ith element, every ith element are equivalent. And by equivalent characters, what do you mean? They also follow the rules of any equivalence relation. So like A equal to A, if A equal to B, then B also is equals to A. And transitivity also, like if A is B, B is C, so A means C, right? So that's how they are defined equivalent characters. And by taking the equivalence information from S1 and S2, we need to find the lexicographically smallest equivalent string of this base string. Okay, we need to return that value. So if you see, try to understand this examples. S1 and S2 are given two strings. P is equivalent to M. Okay, so base string has the value P. Now, among P and M, definitely M is the smallest. So it is the lexicographically smallest. So we write M instead of this P. We replace this P by M. Okay. Now A is itself the most lexicographically smallest. So A, we cannot replace it in any way. Okay. So similarly, we try to see which are the other lexicographically smallest characters, and we replace each element of base string with that lexicographically smallest character and get our output. So first write the problem on your own and then continue with the video. I will take this example. This is some good example. I will take this and let's discuss how to approach that. So let's just start. So we have S1 equal to Leetcode. Okay. We have S2 equal to programs. Note that they both must be of the same length. And we need the base string. We need to translate the base string, which is source code. Okay. We need to translate it. Now you see, they L and P are equivalent here. So I am writing L and I am also writing a P. Okay. And I am just representing them by an edge if they are equivalent. L and P are equivalent here. E and R are equivalent here. Let's write E and let's write R. They are both also equivalent here. Now E and O are also equivalent. So let me connect E with O also. T and G are equivalent. So let me make another component where T and G are equivalent. Okay. C and R again are equivalent. So I place this C here. Again, O and A are equivalent. So O and A will come here. D and M are equivalent. So we don't have D and M anywhere, right? So we make a separate component for D and M are equivalent. E and S are equivalent finally. So you have E connected with S also. Okay. Now by transitive relation, it means that if S is equivalent to E is equivalent to O, and O is equivalent to A. Now you see how many components we have. So we do by trying to understand this type of equivalence relations, you will already get the information of a graph. Now in this connected component of the graph, which is the smallest character? Which is the smallest character lexicographically? It's A, right? So also you know that if S equal to E equal to O equal to A, then S also is equals to A, right? Yeah, because of the transitive relation. So any element of this component will translate to A. Any element of this component will translate to A. What about this? Any element of this component will translate to D. Okay. Any element of this component will translate to G. Any element of this component will translate to L, because L is the lexicographically smallest. Okay. So how do we transfer this S? We will see, as we will get S here, we can start a DFS and go through all the nodes and try to find which is the minimum one. So we will get that corresponding to S, we get A. Corresponding to O, we again get A. Corresponding to U, is there anything for U? See, we don't have anything for U, so it remains as it is. There is R. Okay, R is equivalent to A here. Again, you can traverse from R to A. Then again C, we have C is again equivalent to A. E is also equivalent to A, C again, O again A, D is remains D, and E again goes to A. So this is our answer which we will have, and you can easily understand how to do this. We need to construct this graph and perform a DFS starting from every element of this source code of the base string, and we just need to return the answer by just adding the strings. Okay, so yeah, this is quite simple, quite easy. You can also look for a union find algorithm. If this is basically, if you know union find already, this is a simple application of union find. I am not doing it because both have the same time complexity, O of m plus n. We will discuss that how it's coming, O of m plus n. So yeah, it's really simple. It's linear time complexity you're solving. You cannot optimize any further. So let's discuss one approach only. So let's try to code it out. The approach will be, first we need to form the graph. Okay. So now what we do is simple. We find n, which is the size of the string. We have an adjacency list. Generally, I use vector of vector, but I am using vector of set here. Why so? Because there may be duplicates. I mean, you may have a very large string and there may be multiple A corresponding to, let's say, B. Then there will be multiple mappings. So set will store that as a single element. Now there are, of course, at max 26 characters. So this graph is of constant size graph. So that's very beneficial. You can traverse through the graph in constant time every time. Okay. So what you need to do now, you need to go through the elements one by one. Okay. What you can do, you just convert this is, you just convert all of these characters to simple integers, right? So you get two nodes u and v in that way. You get two nodes u and v. Make it v. Yeah. So what you do now, adjacency of u dot insert, you get v. Also you get adjacency of v dot insert, you get u. Yeah. So you do get it, right? You have the graph which is ready now. So what you need to do, you now need to iterate through the base string. You keep an answer variable, string answer. Each character of the base you will process and add it to the answer. So you just need to iterate through the base string. Okay. So you have base string dot size. You could have also done auto iteration. So yeah, you could have done that. So what you need to do here is get the character in the form of that integer. So base star of I minus a, you get this, right? So after getting this, what you need to do, you do int c1. So it will find minimum. You write a function find minimum, which will take this adjacency list, take this c and tell you what is the minimum character corresponding to this c. We will implement that. And you just, what you do, you just add answer plus equals to this c1 plus a, right? Because it is a character, c1 is now an integer, and just return answer. Okay, I think you did understand what I did here. I just created the graph. I am processing each element of the base string, converting that to the smallest possible character and adding it to the answer. So how to convert that? We need to do a DFS as I already taught you, right? Explained you. So uh, how to do this? Let's write the function first. Vector of set of is adjacency list. Okay, I have this integer c. So what I can do is that I can have a minimum value which is initialized as c as at first. Then I can do a DFS traversal. which will have the adjacency list. It will have the starting vertex. It will have the answer. It will also have a visited array, right? It is always important. So let's make a visited array also, whether a node is visited or not. So if you don't know DFS, just quickly understand that. And yeah, I think we can start with the DFS. It will be a simple, very basic kind of thing. Don't need to do much here. This is the starting vertex. At first, I took the starting vertex. I have the minimum answer, and I also have the visited vector. I am passing this vector. Okay. So yeah, we do have it. All I need to do is now starting vertex is already visited, and yeah, I need to update the minimum of this starting vertex and this, whichever is minimum. I'm just iterating all the nodes. I'm traveling through all the nodes of the graph and taking the values, whichever is minimum. I'm storing it in the minimum, and I'm just returning it. So uh, what we need to do now is go through the adjacency list, right? Go through the adjacency list. So adjacent to this starting vertex, go through all the vertices. Okay, and when you go to the vertices, if that vertices is not visited, if it is not visited, what you do is simple. You call DFS again. That's how you do DFS. That's a recursive function. This starting vertex is V now. This mn will remain mn, and this is visited. Okay. So you do have it. Yeah. You have implemented it, and you see, just try to run it and check if it's working. Okay. So I made a visited n, right? So this is 26 characters. This will be 26 characters. Yeah, so let's try to run it now. We are getting a wrong answer. Let's see. We can see the output is parser, so it is not changing at all. So why it is happening? It's not changing at all. So okay, this minimum value is getting changed, right? So I need to pass it by reference. It's very important to do that. So yeah, now this should be fine, because it's creating a copy of the variable and then it's returning the copy. It's not passing it by address. It's not going to the address and changing the value. That we need to do, right? So we do have the accepted thing. Let's try to submit it. So yeah, we do have the accepted thing. You may try to see that like it's only beats 25%, but don't bother about that. You try to analyze the time complexity on your own. You're creating this graph which takes O of n time. Okay, you take O of n time to do this. And this whole graph is of constant size. So every time you are taking a constant amount of time. Okay, so you are just taking O of 26 to traverse every time. And this base string is O of m, which you are traversing, so it's O of m. So it's nothing but O of m plus n, which is linear time. You cannot solve more faster than this. What you can do is perform a union find. That will not that maybe give a 1 millisecond fast, but it will not be much. So what you can do in union find, you just union. It's quite simple. You just union every element of Si and S, and you just find this value of base tier. Each element of base tier, you just find and add to the answer and return answer. That's all you need to do. If you know union find, you can just go ahead with that. It is of the same linear time complexity. I'm not doing that. So yeah, that was all. That was all for this problem. This might be a new problem to you if you have not done graphs on strings before. Otherwise, it's a really common kind of variation of the graph problems. So yeah, that was all for this problem. This was definitely a medium problem, but I hope your day is going to be really easy. Thank you so much.